Sir, what about the mid important questions?
I will give it the last of this class.
Okay.
So this is the exam point of view. This is a very important topic. Design of screw jack. Regularly, the question asked based on the design of screw jack may be asked for the derivation, may be asked for the numerical. So if you perfect with the derivation, easily you can solve the numerical problems also. Design of screw jack. Okay. So in this, before the designing, few points you need to remember. First one, screwed spindle having square threads. So this is a screwed spindle, this portion. This is the pointer is moving here. That is a screwed spindle. Okay. This spindle having the square thread. The shape form is square threads. And nut and collar for the nut. Nut, this is one nut is there. For this nut, one collar is there. Second point. Third one, head at the top of the screwed spindle for a handle. This is the one. The pointer is moving here. Here pointer is moving. That is the head for the handle. And the cup at the top of the head. Here the top, the cup is appearing. Cup is for the sustain the load. And body for the screw jack. This whole assemble is referred as a here body. So before designing these points, you need to remember few points. What is called what, where, what part we are giving the name, like that. Okay. And here some other dimension parameters. DC is the core diameter. DC is the core diameter. D naught is the nominal diameter, right? So this all whatever the physical parameters appearing on the screen, that all things you need to design. And whatever the image is appearing on the screen, this image you need to draw on the answer sheet when the question is asked for the design of screw, whether it is a numerical or design procedure, right? So these are the few points. Now in design procedure, first point in design procedure, first point, finding out the core diameter. Finding out the core diameter, it is denoted by D suffix C. Here you can see on the image D suffix C, core diameter. Core diameter you can see on the screwed spindle. Okay. So DC first of all we need to find out. So see here, the load is applying here. It means nothing but whatever the part we are lifting, that is going to place here and rotating this handle. So the reason the load is vertically acting downward on the screw jack. So that's the reason the screwed spindle may be subjected to compressive stress. Compressive stress, that is nothing but load by area. Load PR, here PRW, nothing but W by area. So which area we need to consider? The part of whichever subjected to compressive, this part. Okay. So that is the reason here area we are writing pi by 4 into DC square. DC only that we need to calculate, right? Now with this we can write one equation, that is PRW equal sigma C into pi by 4 into DC square, right? With this equation, DC is going to calculate it. DC is going to calculate it. Okay. With the reference this one, the other parameters are going to selected from the table: nominal diameter, bolt diameter, nut diameter, major diameter, P, pitch value, bolt height, may be selected from the table. Otherwise, now the second point, torque required, torque required, to lift the load. Lift the load. Okay. So torque required to lift the load. Lift the load, I am giving the title as a T suffix 1. T suffix 1. How much T suffix 1 equal? We are applying the force P into T by 2 into D by 2, right? So here, what is P? P is we are applying. So what we are applying here to lifting the load. So already we discussed the one equation, force required to lift the load. Already in the previous class also we discussed this one. Already this equation you studied in the kinematics of machinery, that is W tan alpha plus pi. This already you discussed in the kinematics of machinery, right? So that P value I am writing. P is equal to W tan alpha plus pi. Pi is the pressure angle, alpha is the helix angle, W is applied load on the screw jack, right? And D is the its mean diameter, right? So this is the equation. Okay. Under this equation, shear stress due to the applying this torque to lift the load, there may be shear stress. There may be shear stress. In the second point, again one subtitle, shear stress due to this lifting load. Lifting load. So where is the shear stress? In the screwed rod portion or nut portion, screwed spindle portion, there may be shear stress due to this torque. How much that one? So here the screwed spindle considering as a one shaft, solid circular shaft, right? So torque transmitted by the shaft equation already we discussed in the design of shaft, pi by 16 into sigma s into T C power 3. Okay. So with this sigma s shear stress is going to calculate it. T1 into 16 into pi into DC power 3. This one is going to calculated in terms of megapascal. Right, we calculated this one. And now in this title only, in this second title only, another subtitle, second subtitle, that is compressive stress induced. Compressive, compressive stress. So compressive stress due to lifting the load. Lifting load. Right. So compressive stress means general equation, load by area. Area means pi by 4 into DC square. Right. So the answer will get in terms of megapascal. We calculated this one. Shear stress due to lifting load, compressive stress due to the lifting load. These two we calculated. Right. Now third point. Third point. Third point. Finding the principal stresses. Finding the principal stresses. Why I am calculating the principal stresses? In the previous topic, torque required to lift the load. Due to this torque requiring to lifting the load, while lifting the load in the screwed spindle, there are two types of stresses are induces. First one is a shear stress, second one is the compressive stress. So due to this reason, I am now calculating the third point as principal stresses. Okay. So principal stress is maximum principal stress. Maximum principal stress. Already you know aware about the you have aware about this equation. Principal stress sigma c plus square root of sigma c square plus 4 shear square maximum, and maximum shear stress. Maximum shear stress is 1 by 2 square root of sigma c square plus 4 shear square. Okay, you will get the answer in terms of megapascal. In terms of megapascal. Now, after getting these values, this one is called here induced compressive stress. This one is called here induced shear stress. Okay. So here finally what we have to do, induced stresses, induced stresses, induced stresses always should always less than the permissible stresses. Permissible stresses. So these induced stresses are nothing but that just now we calculated this one and this one, right? This one, this one will give in the question. Permissible values will be given in the question. We need to compare here. If you get the answer like this, less than this value, then your design is safe. Whatever the previous points you calculated, all points are under safe condition. That is a third point. Now in design procedure, fourth point. I'm telling the fourth point now. Finding the height of the nut. Finding the, just wait. Wait a minute. Now, fourth point. Finding the height of the nut. Height of nut. So where is the nut? You can see here nut. It is indicating here. This is the nut portion. So this is the nut, right? So here finding the how much height. So height is denoted by here small h. Here it is indicating on the image small h, right? So this height I am calculating. So to calculate this height, see here, while rotating the spindle, we are applying the force here manually. So while applying this force, due to the rotation of this screwed spindle, the spindle is going to move upward direction, right? So that reason there will be a bearing pressure involving here, bearing pressure involving. So by considering the bearing pressure, by considering the bearing pressure, what is bearing pressure? Bearing pressure is nothing but pressure, like a pressure load by area, load by area, right? So what is the area here? Load by area. So what is the area here? Area, this portion where the spindle and screw is going to contact takes place, that area, right? So that area I'm writing here, bearing pressure equal load by area. So for one particular portion, one particular at one third particular threaded portion, I'm calculating pi by 4 into pi by 4 into d naught square. See here, d naught is the outermost layer, dc is the inner core, right? So d naught square minus dc square. So this is the equation for one threaded portion, contact between the nut and screw, right? Like this, how many threads are there? N number of threads are there. We don't know. So that reason n number of threads I'm writing here. Bearing pressure, right? With this bearing pressure, n number of thread is going to calculated, right? Now height of the nut is n number of threads into pitch. Height of the thread is n number of threads into pitch. Pitch means what? Distance between the one successive thread, right? Distance between the one thread to another thread is called as a pitch. Like that, how many pitches are there? N number of pitches are there. That is n in here. So that gives the height of the nut. So this n is just now we calculated here, right? So this is the fourth point. Now fifth point. Fifth point I'm calculating now. Now fifth point, checking purpose here. Fifth point, checking. So what we are checking here, stresses, checking the stresses here, stresses in a screw and a nut. Checking the stresses in a screw and a nut. Sir, already we calculated again. Why you are telling this one? But why see here? Only threaded portion I'm telling. Only threaded portion, right? So previously we calculated considering the overall rod thread, both we consider. But now I'm just considering the only threaded portion. Only threaded portion only. Threaded portion means suppose this is the square thread, right? This is a square thread. Okay. Now I'm considering only this threaded portion, screw and for nut stresses. So what type of stresses are there? Only shear stress is there because suppose this is the screwed spindle, another thread is going to maybe like this from the nut, right? These two are going to contact takes place here and here. So this is the diagram I'm drawing here in this region. In this region, okay, don't get confused. When thread and when the bolt and nut contact takes place between the thread to thread, because of metal to metal contact, there will be a shear stress. There will be a shear stress, right? So shear stress involving here. So that's the reason sigma s I'm writing per screw, per screw. So for screw means see here, core diameter is a very important. For screw, core diameter is a very important. Generally stress means what? Load by area. Load by area. So load by, what is the load here? Always this load only we need to consider. Load by area. What is the area? So it's perimeter. It's perimeter because I'm not considering the solid portion. Only along the circumference of the rod I'm considering. So that reason pi into dc into dc into t, dc into t into n number of threads. So it means what is the meaning of this t? dc means core diameter, t means tooth thickness. This one, t means tooth thickness, right? That is the t. So this is the stress, and where the t, tooth thickness, is nothing but pitch by 2. Tooth thickness is nothing but pitch by 2, right? Now shear stress for the nut, for the nut, for the nut also same equation. What is the equation? Load by area. Stress means basically load by area only, right? So load by area. So what is the area here? So area I'm writing load by area. So nut means, see here, the nut. This is the nut portion. The outer one is a nut portion that is going to taking here contact with the core diameter. Sorry, outer diameter. Okay. So that is pi into d naught into t into number of threads. Okay, where t is a to thickness, it is empirical relation pitch by 2. It is its empirical relation is a pitch by 2. Okay, now what we are doing here, checking. These are the stresses are called induced stresses. These are called here induced stresses for the nut and screw only threaded portion. Try to understand. I'm telling here nut and screw only threaded portion, not along the solid rod. Okay. So this induced stresses should always less than the permissible stresses. This condition should satisfy. This is the fifth point. Now sixth point. Sixth point, finding the inner diameter, finding inner diameter D1, inner diameter D1, comma outer diameter D2, comma thickness T1 for the nut collar. Nut collar. So where is the nut collar? So this is the nut collar. This is the nut collar. For this nut collar, the dimensions are D1. Here you can see the D1. Here you can see the D2, D2, and here you can see the T1. These three parameters we are calculating now. These three parameters we are calculating. First one, D1. First one, D1 I am calculating. So for D1, considering the tensile stress for the nut, because while we are rotating this spindle, the screw is going to subject it to compressive. Screw is going to subject it to compressive because this nut is pulling the screw in the above direction. So nut is pulling means automatically this nut is subjected to here tensile stress. So that's the reason tensile sigma t equal, what is the equation generally? Load by area. Load by area, right? So what is the area here? Load by area. Area pi by 4 d naught square. That is the tensile stress. With this equation, W we can write as a pi by 4 into d1 square minus d0 square into sigma t. So this equation we can call here tensile resistance for the nut collar. Okay. And second, in this only the second point, d2 I am calculating. So d1 is going to determine here. Okay. Now second point, d2 I am calculating. So d2 means here it is. So this nut is coming outside here. This nut is this screw is coming out here. The nut is going to subject it to here compressive force. So due to that, compressive stress is going to involve here. That is load by area. That is load by area. What is area here? The area. So while taking the area, d2, d1. At the d1, while calculating the d1, d1 and d0 we need to consider. While calculating d2, d2 and d1 we need to consider. That is pi by 4 into d2 square minus d1 square. So d1 just now we calculated here, right? Here d2 is calculated. So w equals sigma c into pi by 4 into d2 square minus d1 square. d2 is determined. This equation is called tensile compressive resistance for the nut. Okay. Now third point. What is the third point here? T1. Third point is a T1. T1. What is the T1 here? Thickness of the nut collar. Thickness of the nut collar. So this is the thickness. How much thickness we need to maintain? That is the question here. Thickness of the nut collar. So while we are applying the force here, so this spindle is going to rotate, right? So due to the rotatory motion, the nut and screw threaded portions between here that are contact takes place, and due to that rotation, the threads are going to subjected to shear. Try to understand here. Threads are subjected to shear due to metal to metal contact while it is rotating, right? So shear stress, shear I'm telling here, so that reason shear stress is going to involving. So that is shear stress is equal load by area. Load by area. So what is the shear area here? The shear area I'm writing area, that is pi into d1 pi into d1 into t1 into t1. That is the shear stress. So with this equation, W equal sigma s into pi into d1 into t1. So this equation called here shear resistance for the nut collar, right? So with this equation, T1 is going to determine. With this equation, T1 is going to determine. Here, all parameters are in mm, right? So this is the sixth point. So in sixth point, again three sub points are there, right? Don't forget. Now I am calculating the seventh point. I am calculating the seventh point. In seventh point, again three parameters are there. In seventh point, again three parameters are there. In the seventh point, first subtopic is the dimensions for the head. So which one is the head? Where the handle is attached here. So this is the head. The where the pointer is moving here, that is the head. Okay, dimensions for the head. So dimensions for the head diameter is d3. The head diameter is a d3. Okay, its empirical relation is 1.75 1.75 into d naught. First point, this is the one. Okay, now second point, seat for the cup. Here the top cup is appearing. This is known as a cup. So for this cup, one seat is required. Okay, so this seat diameter is equal to seat diameter equal to same nut the head diameter d3, same head diameter d3, but this head diameter, the seat diameter is somewhat chamfered. Okay, here chamfering you can find here, right? Accommodation for the pin. So that is the third pin. What is that? Pin diameter, how much? Pin diameter is the d4. Here seat is provided as d3 diameter only, but the seat is provided with the chamfering here. This chamfering for the accommodation of the pin. Okay, so this pin having the diameter d4, the pin is having the somewhat diameter that is d4, that is empirical relation d4 equal d3 by 4, d3 by 4. This is about the seventh point in design procedure of the screw jack, the seventh point, right? Now eighth point. The eighth point is the eighth point is eighth point is finding the finding out the torque T2, finding out the torque T2 to overcome the friction, to overcome the friction, friction. Okay, so where is the friction? Friction you can find here. Friction you can find the here and in this region. Friction we can overcome here. So overcoming the friction T2. So T2 is what is the equation? Mu into W into mu1 into R, right? See, this is the equation W into mu1 into R, where R is the mean radius, where R is the mean radius, where R is the mean radius. Okay, so if the question asked by considering uniform pressure theory, if the question is asking uniform pressure theory, so this mean radius is 2 by 3, 2 by 3, where the overcoming the friction, where the friction involving here the handle, at the handle the friction is involving. Okay, so what is the dimensions here? D3 is there and D4 is there. So that is R4 power 3 minus R3 power 3 by R4 square minus R3 square. This is the when the question is asking about the uniform pressure theory. Okay, if the question asked uniform wear theory, for the radius, mean radius, so this equation becomes R4 R4 plus R3 by 2. Okay, so this R values you need to substitute here. One R value 2 by 3, R power 4, R4 power 3 minus R3 power 3 by R4 square minus R3 square. This is the equation when uniform pressure theory consideration. This one we need to consider when uniform wear theory consideration. These two values are the represents the this mean radius. Okay, this is the eighth point. Now ninth point. Ninth point, total torque required here. Total torque, total torque, total torque T, nothing but torque required for the lifting the load T1 plus torque required overcoming the friction T2. T1 at the beginning we calculated. T1 at the beginning we calculated, that is P into D by 2, just we calculated at the beginning. Now T2 is the overcoming the friction. T1 due to the T1 is due to over lifting the load. T2 we are writing because to overcome the friction, right? That gives the total torque, right? So why we are calculating the total torque? This total torque is applied by the human being. Worker, the workman is going to apply his force here. That is the total torque, right? Total torque is applying here. So due to applying this total torque, this lift is going to this jack is going to lifted in this direction. While lifting, two phenomena are involving here. First one is the lifting the load. First one is the lifting the load, and while it is rotating, he will feel the one friction is there. So that's the reason slowly this rod is going to move. That is the overcoming the friction. So what we are doing here, he has to apply the total torque here. That is the 1 plus 2. That is 1 plus 2. That is the total torque. So with this total torque value, we are going to calculate how much length we need to maintain for this handle. How much length is going to we need to maintain for this handle, right? So for that, length of the handle is total torque by 300 to 400 newtons of force. So what is 300 to 400 newtons of force? This is the force applied by the our human beings. An average man can apply the force average on an average 300 newtons to 400 newtons. You can select the 300, you can select the 350, you can select the 400, your wish. Okay, so on an average, one man can apply the force of this much of magnitude. So that gives the length of the handle. Length of the handle, nothing but how much easily means easily we can apply the force means gripping purpose. So if you provide the lesser handle here, lesser length of the handle, that means you need to apply the heavy effort, right? So if you maintain the larger length of the handle, what happens? There will be bending effect, right? So that reason, to avoid this difficulty, one optimal length of the handle we need to maintain. So for that, on average, the human being, how much he can apply the load, that load value we are taking, with that we are getting the one length value. This length value will give the handle length for the gripping purpose, right? So that is the ninth point. Now tenth one, diameter for the handle. So this handle diameter, it is denoted by capital D. Diameter for the handle, capital D. Okay, so this one we are calculating. So while we are applying the force here, there may be subjected to this handle bending. So bending phenomena involving here, because um, over here, because of heavy friction, this head is not going to rotate properly, even though you are applying continuously force. So at that time, what happen? There may be chances. There may be chances for the this handle bending takes place. So bending, what I'm telling, bending. So bending means obviously here bending stress is going to involve. So what is the stress? Stress equation general meaning load by area. So one thing you need to bending means this equation should not consider. Bending stress means bending moment by section modulus. This equation we need to consider, right? So bending moment, M is bending moment. What is the bending moment? Load into distance. Bending moment is load into distance, right? So here, see, always I'm writing the capital W. Capital W means at the top what we are applying here, lifted body. Okay, so load into E. So E is nothing but here this length of the spindle, right? Now what is section modulus? Section modulus, here the dimensions of the handle, if you see, this is appearing in a D. D means it is having the circular. D means circular only, right? So section modulus for the circular section, that is pi by 32. Section modulus for the section, circular section is pi by 32. What is the equation? D power 3. So m equal pi by 32 into d power 3 into sigma b, right? With this equation, D, capital D is going to determine. Capital D is going to determine, right? Now height of the head. Height of the head is denoted by capital H. 11th point. Height of head. Height of head, it is denoted by capital H. Okay. The relation, empirical relation 2D. This much we need to maintain magnitude, right? Now 12th point. 12th point, checking. 12th point is the checking. What we need to check here? Buckling load we need to check. Buckling load we need to check. Buckling load is a critical load. Already you learned this topic in a strength of material, critical load or buckling load for the columns. Okay, so buckling load denoted by WCR, right? So here rankings, one formula is there already discussed in the mechanics of material. That equation I'm writing here. WCR crushed area into yield strength into 1 minus yield strength by 4 into C into pi square into Young's modulus pi square into Young's modulus into effective length by radius of gyration square, right? So where AC is a compressed area, sigma y is a yield strength in megapascal, y is the yield strength in megapascal, C is the end flexibility coefficient, end flexibility coefficient. Okay, so this coefficient in columns and sets we have four different sub columns. One is a fixed, another in free, right? One both ends are fixed, both end are fixed. One end is fixed, another end is hinged, both ends are hinged. So these are the four conditions are there in studs and columns, right? Now here in this case we are considering the one end is fixed, one end is free. Okay, so because one end is fixed means this is a fixed condition, fixed to the load whichever is lifting up, and another end is a free, another end is a free, right? So for this the C value is 0.25. 0.25. I'm not taking my own. These already values are there in the mechanics of material. That values I'm taking here, right? And capital L is the effective length. Capital length is the effective length. Capital L is the effective length, right? And the K is the radius of gyration. The K is relation here 0.25 into D suffix C, core diameter 0.225 into D suffix C. Okay, and where it E is the Young's modulus, E is the Young's modulus, megapascal, right? So all values you need to substitute here. You will get the WCR. You will get the WCR. So what is WCR? Critical load, buckling load. WCR is a critical load, or we can call as a buckling load. Here, what we are doing, main intention is checking here. Buckling load, we are checking here. So buckling load, we are checking. Now we calculated the buckling load. This buckling load should always, whatever the you are getting the value now here, this value should always get the greater than the what we are applying here. What we are applying here. That is for especially for this condition. Always what I said, whatever the induced stresses, induced values should always getting the get less than the permissible value. Na? Here, whatever the calculated value here I'm getting, that is greater than the whatever we are applying here. W means applying load. Applying load on screw jack. Screw jack. Okay. So this condition you need to satisfy. Then only the whatever the previous parameters, number 1 to 2, number 11, whatever the parameters we calculated, all are under safe condition. That condition you need to write. Hence it is satisfied. So the design of screw jack is under safe condition. Under safe condition is everything you need to write about. If the question is asking for the derivation part, you need to draw this diagram and one by one parameters how I'm calculating 1, 2, 3, 4, 5, 6, 7, 8, 9, like that you need to show, right? Otherwise you won't get the good score. Now next one is the last point, efficiency we need to find. Efficiency of this screw jack. Efficiency of this screw jack is nothing but torque required and ideal condition by actual torque. Torque required and ideal condition by T naught is the ideal condition. T is the actual condition, right? So what is the torque required? This is the general equation T W into tan alpha into D by 2, and W TA means W into tan alpha plus pi into D by 2. So in actually pi involving, in ideally pi is neglecting. That is only the difference, right? W D by 2 gets cancelled. Tan alpha by tan pi plus alpha. This will give the efficiency of the screw jack in terms of percentage. So for this, the question asks for 15 marks. This entire 13 parameters you need to remember. Okay. So one problem we'll discuss. This is a problem you can expect for the mid exam, second mid exam. This problem you can expect for the second mid exam. Just wait. Just wait. అదే తీసుకొచ్చి దాంట్లోనే పెట్టిన చూపించుకో 5 minutes లేకపోతే క్లాస్. Right, Amma. This is the problem you can expect for the mid examination, second mid exam. So given that I'm ready, given it up. So listen, whenever the problem given about screw jack, if you see the term screw jack means immediately you need to draw this diagram. Immediately you need to draw this diagram. Otherwise, you cannot get the good means exact max. How much you are expecting that marks you cannot accept. What is that? You cannot see that score. Okay. So a screw jack is lifted to 80 kilonewtons. Here the load is given 80 kilonewtons. So W value is given 80 kilonewtons. So what is question asking? We need to lift a load 80 kilonewtons of a height H1 of a height H1 400 mm, right? Now elastic strength of a screw material. Screw means for the bolt in tension and compression. In tension and compression, elastic tension, elastic compression, 200 megapascal, right? And in a shear, elastic in a shear for 120 megapascal, right? These two values for screw portion, right? And a material for the nut, phosphorus bronze material for which elastic, see here, elastic limit may be taken as 100 megapascal in tension and 90 megapascal in compression, 90 megapascal in a compression and 80 megapascal in a shear. 80 megapascal in a shear. And the bearing pressure is given question itself. 18 should not exceed 18 Newton per mm square, right? Question asking design and draw the screw jack. Design and draw the screw jack. So design and draw means entire thing what we did 13 points here, that all 13 points you need to calculate. Nothing but if you perfect with the derivation part, no need to practice this numerical also, because what I practice in the derivation, same things I am going to copy here. That's all. Same thing I am going to copy here, right? So the design, one hint is given. Design hint. This is nothing but hint. Include the screw, nut, and handle, and cup and body. That only we design just now, right? So the first one, design for the screw. First point, design for screw design for screw, for spindle. I'm doing nothing but in design procedure. First point what we calculated, we calculated the core diameter. We calculated the core diameter in core diameter in design procedure. We did this one, first one. So by considering the compressive stress in design procedure, what we did, compressive stress is equal load by area we consider, and load equal to compressive stress into compressed area. So what is the area? Pi by 4 into dc square. This one we taken, right? So here compressive core diameter we calculated. So core diameter means, just write down here. I'm writing 80 into 10 to the power of 3. 80 into 10 to the power of 3. Compressive stress. How much the compressive stress we need to take? Compressive stress is how much? Here elastic and compressive both are given, tensile and compressive given 200 megapascal. These values are under elastic limit, not pure tension, not pure compression, right? So to get this one, factor of safety we need to consider here. So generally factor of safety I'm considering, assuming as a 2. Factor of safety assuming 2, right? So tensile strength, compressive strength 200 by factor of safety. So 200 by factor of safety is nothing but 2, that is 100 megapascal. 100 megapascal. Now compressive stress is a 100 megapascal, right? So here I'm writing 100 megapascal into pi by 4 into dc square, right? So what is dc? Tell me the value of dc in mm. Everything is appearing on the screen. Just tell me the value of dc in mm. This problem coming in the second mid examination, Babu. You people focus on this problem and design procedure, because regularly the question is asking in the external examination. Very important topic for external exam point of view. Directly you can get the 15 out of 15 marks. So there is reason we focus on the classes. So tell me the DC value. I'm expecting the answer from all students. How much DC value? Are you there or not, Babu? Nobody is responding.
Sir, 31.91.
Oh, just wait a minute. Somebody kept message. Sorry, important for internal question. I will give in the end of this class. Just wait. How much
Sir,
amount, please?
31.91.
31.91 means, so 32 round figure I'm writing. 32 mm. Right? Now, whether this diameter we are getting, whether is under safe condition or not, we need to select from the table again. Right? So the table I'm showing here. So core diameter here. Core diameter is the core diameter DC. Okay. So DC, how much we got? Round figure 30 here. 31.91 means 32. So 32 here, 31, 32 is there. 31, 33 is there. 32 not there. So 32 is not there here. Okay. Forty-six. So 33 round figure we are taking. 32 is not a thing. 33 we are taking. Okay. And the rest of the values, by seeing this one, rest of the values, you need to select like this. So whatever the values are appearing here, that all values I'm writing. 36, 36, 36.5.
Sir, in exam they will give the values.
They won't give. We need to remember some values. We need to remember. See here, in examination, the examiner not going to see this answer whether you got the exact answer or wrong answer. He will focus on the units and design procedure, because what I'm telling, you can select your own value. You can select your own value. Actually, you got the 31.9, right? 31.9 mm you got. What I said, round figure, I'm taking the 32. I'm taking, but 32 is not appearing there. You can select the, what I said, you can select the 33, right? Here you can select, now you cannot, you can select the not 33, you can select the 43, 50, near about values. If the 33 is not appearing there, you can select the 38, 39, 40, up to certain value limit. Okay, so it means somebody may select the 33, somebody select the 38, somebody select the 30, 40, like that. So the results are going to not exactly, the result are not going to come exactly, because exact answer is, suppose exact answer is the 34, suppose, right? So 34 is the exact answer. Somebody may get the 32, 33, 43, like this somebody will get. So near to this value, the examiner will see that whether it is coming near to this value or not. You should not exceed the double digit. Here double digit answer is coming, exact answer. So it means your answer should not come 100, 101, 103, 150, 2000, like that. So it may double digit. It means he will going to consider the answer, because here some points are there. You are considering your in your own way. So the reason what I'm telling, assume any suitable value. So here factor of safety I selected 2. Somebody may select the 1 factor of safety. Somebody may select the factor of safety 3. Somebody may select the 4. Depends on the designer. Okay. So if the data book is not provided in the examination, so you can select your own values. Some any 4 values you remember roughly. Always substitute, any problem asking, the substitute that 4 values only, right? So here nominal diameter d naught, nominal diameter d naught, 46 I'm taking 46. Pitch of the thread, pitch value I'm taking 8 mm. From the table only I'm taking these values. Table only I'm taking these values, 8 mm. And mean diameter is dc plus d naught by 2, dc plus d naught by 2. So d naught how much we got, d naught 46, dc how much we got, 33 we consider, 33 by 2. How much this is mean diameter? How much this mean diameter? Tell me the fast bow.
39.
39, right? Now see here. Okay, we'll discuss this problem tomorrow. You people be present in the next class.
Sir, important questions you told you will give today.